Today we are starting a new chapter. It is the chemical kinetics. We know that chemical reaction have the 2 points of concern. One is the feasibility of the chemical reaction, and feasibility of the chemical reaction is dealt by the thermodynamics. A reaction is feasible if delta G, that is the Gibbs free energy, is less than 0, that is negative, at constant temperature and pressure. And another point of concern is the speed of chemical reaction, and it is dealt by the chemical kinetics. So chemical kinetics deals with the reaction rate and its mechanism. First we discuss rate of reaction. Suppose we have a reaction, that is R refers the reactants, and after reaction it gives the product P. The concentration of the reactant is represented by R within the square bracket. This square bracket refers the concentration, say in terms of molarity, and unit is mole per liter. So at time t equal to T1, suppose concentration of the reactant is R1 and concentration of the product is P1. 1 refers the time T1, and after some time at time instant T2, the concentration of the reactant becomes R2 and of the product becomes P2. So change in concentration of the reactant will be equal to the final concentration minus initial concentration, and for reactant this will be a negative value. Similarly, change in the concentration of the product, it will be equal to final concentration of product minus initial concentration of the product, and this value will be positive. So we can define the rate of the reaction, and rate of reaction is always positive. For that, if we refer the rate of reaction with a small r, this will be equal to the negative for the reactants delta R by delta T. This is the change in concentration per second, or same can be specified as change in the concentration of the product per second. Therefore, unit of the rate of reaction is the concentration divided by the time. Unit of concentration is mole per liter and time is second. So unit of the rate of reaction R is mole per liter per second. Here this R refers the average rate of reaction. If delta T is very small, approaching to 0, then this rate of reaction becomes instantaneous rate of reaction and can be written as minus dR by dt, and it will be equal to dP by dt. Let's take some examples. First example is we have to write the rate of reaction for the given expression. So rate of reaction is equal to the negative of the rate of change of concentration of the reactants, and it is delta concentration of Hg divided by delta T. Similarly, chlorine is also reactant, therefore it is minus delta concentration of chlorine divided by delta T, and it is equal to HgCl2 is the product, and we can write the rate of reaction in terms of product as change in concentration of the product HgCl2 divided by delta T. Second example is Hi gives H2 and I2 on dissociation. Here point to be noted that the stoichiometric coefficient of the Hi is not unity, it is 2. For the reactant or product having the stoichiometric coefficient not equal to 1, the rate of appearance or disappearance of the reactant or product will be the change in concentration divided by the stoichiometric coefficient. So we can write the rate of reaction R is equal to negative for the reactants delta, and the reactant is Hi concentration divided by delta T, and this whole divided by the stoichiometric coefficient, that is 2, and it will be equal to then change in the concentration of the product, that is H2 divided by delta T, and similarly change in the concentration of the another product, that is the I2 divided by delta T. So we can write it is minus 1 by 2 delta Hi by delta T, that is equal to delta H2 by delta T and delta I2 by delta T. So in this case, if the stoichiometric coefficient is not equal to 1, then we have to divide the rate of change of concentration by the stoichiometric coefficient to get the rate of reaction. For third example, the rate of the reaction can be written as negative of the rate of change of concentration of the reactants, that is minus 1 by 5. 5 is the stoichiometric coefficient of Br ion, and it is delta change in concentration of bromide ion divided by delta T, and it is equal to negative of the another reactant, that is BrO3 minus by delta T. It is equal to minus 1 by 6 of change in concentration of hydrogen ion divided by delta T. And now the product is bromine, so it is 1 by 3 delta Br2 by delta T. And similarly, it is 1 by 3 change in concentration of H2O divided by delta T.